Today we're going to be talking about my personal favorite part in all of chemistry, the atom. Basically, chemistry is all about atoms and compounds. Okay, so an atom is a very teeny tiny thing. Like it's so incredibly small. And it makes, well, practically everything. Well, in our daily lives. Not everything in the universe, but everything in our daily lives. So an atom is like 10 to the negative 10th power meters, which is 1 over 10 to the 10th. It's like a teeny tiny small, like it's teeny tiny. It's composed of three parts: the proton, neutron, and electron. Um, the nucleus is basically composed of the proton and the neutron. So basically, we're going to talk about this more in the next slide, but protons have a positive charge, neutrons have a neutral charge, and the electrons have a negative charge. Anyways, just to give you an idea, like, of an atom, this is not an accurate representation of the atom. An atom is actually, most of the atom is empty space. The electron orbitals are far out, and plus, there are a lot of orbitals. You cannot say the electrons orbit like this. This will be more of like a I don't know, Bohr model type. Anyway, we're gonna go over those later. Um, Basically, there are a lot of shells that electrons can float, can like orbit, and they're far away from the nucleus, like really far away. But we're mainly going to talk about orbitals, shells, electron configuration, and stuff in the next video. This video is just to give you a basic idea of what an atom is. Like I said here, a proton has a positive charge, a neutron has no charge, an electron has a negative charge. So if you think about it, the protons and the electrons balance each other out. This here is a atom of helium. But of course, like I said, this is not accurate at all. Very inaccurate. So this is not what an atom will look like. But this will probably give us an idea, I guess. Basically, neutrons, because they're neutral, they can hold protons together. And there is this thing called isotopes. Because the number of protons determine what element this is. For example, this atom, it has 2 protons. Well, from what we can see, it has 2 protons. And on the periodic table, the number on the top left corner of the element, that is its atomic number. Well, basically what that means is this atom has, like for example, helium, its atomic number is 2. So this atom, an atom of helium has 2 protons. That's all it means. What about neutrons then? Neutrons are atoms can be of the same element, but they can have different numbers of neutrons. Basically, carbon, if we look at carbon, like 12, carbon 12 neutrons, 6 neutrons is enough to hold the 6 protons together. Carbon's atomic number is 6. But there's also like other isotopes of carbon, which is like carbon 13, carbon 14, and etc. So 7 neutrons can also hold together the 6 protons. Because we're always sure that carbon has 6 protons. And then this thing is just the total atomic mass. We will ignore the electrons when we're calculating the total atomic mass, because their mass was so small that for our purposes, we ignore it. But just like you know, they do have mass, but it's teeny tiny. We'll just ignore it. Anyways, this is the total atomic mass, which is the number of protons plus the number of neutrons. In this case, it has 7 neutrons. So add them together, you get 13. 14, same thing. We have 6 protons and 8 neutrons, if I did the calculations correct. Yes. Um, so far, so good. It's pretty simple. And now, like I mentioned, charges. Basically, for an atom to be neutral, what I mean by that is it doesn't have a positive charge or a negative charge. So the charge of that atom is neutral, like not positive, not negative. And in order for an atom to have that, it needs to have the same number of protons and electrons. Because if we think about that, for example, take this atom, helium. It has 2 protons. Helium's atomic number is 2. So in a nucleus, the charge is 2 positive. By the way, 2 positive equal positive 2. Now, in order, actually I'll write it in like positive 2 form. And in order for the atom to be neutral, it will have 2 electrons. Minus 2 equals 0. Basically, if you haven't already figured it out, the way to calculate the total charge of an atom is just by adding like the number of protons and like the total charge of protons and the total charge of electrons. The total charge of electrons will always have a negative sign in front of it. So basically, it's like this. Like, I don't know if you can see that very clearly, but basically it's like this. But we just ignore this part. This atom is neutral. But then, when we're actually looking at a periodic table and talking about different groups and their valence electrons, you would see every group have a specific charge. Every A group. But that's for later. Okay, let's move on. Here, like a hydrogen atom is a very interesting case. It's 1 proton, no neutrons, 1 proton, and 1 electron. Basically, oh, by the way, this is not 100% correct. This is just to be neutral. It doesn't, atoms tend to want to be neutral, but there's a thing that they want more, which is to have 8 valence electrons. What that term means, we're hopefully going to talk about that the video after the next one. But just to let you know, this statement works, but it's not 100% correct. Anyway, in an electron cloud, this is a Bohr model of an atom. So we see orbitals. But this is not an accurate representation of actually an atom. So an electron cloud is where the electron might be. The electron moves incredibly fast. And you cannot tell where the electron is. So the electron cloud is basically like a probability function, like where the electron might be. And later in the next video, we're going to be talking about orbitals. In this case, this electron is going to go in an s orbital, which is an orbital in the shape of a sphere. And basically, in this orbital, wherever in this orbital the electron might be, that is the electron cloud. We can say the electron is here. Not accurate. But this is a commonly used model. But this is not accurate. Well, for this case, for hydrogen, I guess you could say it is, because there is only one shell, and that's in sphere orbital. But I prefer to not see the electron, though the Bohr model insists that we see it. Just in case you're wondering what this thing is, this is the electron configuration. We are going to be talking about that in the next video, or the video after that. Anyway, practically, we've already talked about most of the stuff in this slide, but here's just a quick thing to note. Atomic mass does not equal mass number. Like I talked about, there are isotopes, like carbon with a mass of 12. That's the most common isotope. But there are also, like I said, carbon 13, carbon 40, etc. So basically, the atomic mass is the average mass of all of these isotopes. But the mass number is just the mass number of a specific atom. Sometimes you would also see atomic mass for mass number and atomic weight for like this part. But I tend to use this one, and this is what I was taught in school. So you might see different like ideas and different terminology or words used for these. Okay. We've already touched on this, but this is like a real quick way because the calculation for this involve, for example, carbon 12 is most abundant. There's a lot of these in nature. So basically, this is going to have a higher percentage, and this is going to weigh more than this. It's not where your teacher's calculating test scores. This is you can see this as a test, and this one as like a homework. The test weighs more. So yeah, 12 is going to mean more. But we're going to go into the calculations later. Anyways, for example, if we're trying to do carbon here, and then we wanted to know, for example, I'm saying like how many neutrons are in an atom of like carbon, most likely. So like according to my periodic table, the atomic the atomic mass for carbon is 12.0107. Well, basically it's like 12.01, which is what you will see on most periodic tables. If you go into a little bit more detail, it's going to be 12.0107. Anyways, we round it because, like I said, the 12 mean more than 13. So we round it, it's going to be like 12. And if it's 12.5, we will round it to 13. So it's just like rounding. This is going to be most abundant, so carbon's atomic number is 6. So basically what this atom is going to look like, again, I am using a not like, well, accurate representation of the atom, okay? This is not accurate, but like, just to help you visualize it, it's going to be like 1 proton, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They do not go in this format. In order to hold all the protons together, the neutrons go like inside and stuff. But like it's a 3D model. But for the sake of showing you, I'm just going to draw it this way. And I am not a good artist. Again, I'm using the Bohr model. Carbon should have, yeah. Okay. And before we start, I want to make this as accurate as possible. So, yeah. Let's see. Electron, 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 electron. This is not accurate, but the best I can do is this. We're gonna talk about the shells next time, so don't worry about why there are 2 circles outside. Anyways, this is practically gonna be what the atom looks like. Like this is the most abundant atom in nature. The most abundant, not the most abundant atom. That's gonna be like hydrogen or something like that. I don't know, but like it's the most abundant isotope of carbon. So we round it. Carbon's atomic number is 6, so it's gonna have 6 protons. Minus 6, and then we get like 6. So there are 6 neutrons. Now, say for example, the atomic mass is given. Like we say, there's an atom with an atomic, there's an atom of carbon with an atomic mass of 13. So it's going to be carbon 13. How many neutrons are there? Again, it's 13 minus 6, the proton number, the number of protons, equals 7. So far so good? Pretty simple. Anyways, now let's try to calculate electrons. So before we do that, let's move on to the next slide. Oops. There we go. So there are two ways to write isotopes. So like carbon 13 dash. This is a little dash. You've probably seen me like do this before. Technically, what I was doing here, like, this is not official. Like, I do it, but this is not right. Well, I guess you could say that there isn't much fault in that, but this is not like really good. When you write this, you write carbon, the whole word, or you just do like this. Here we write the proton number. Here we write the total mass, the like mass number, and here we write the charge. In this case, the carbon is going to have a charge of 2 minus, which means it has 2 more electrons than protons. Because if you think about it, it has 6 protons. It has 6 protons, and then 6 electrons went and canceled it out. Normal, neutral carbon. Now there's another like charge, -2, which means that the carbon atom gained 2 gained 2 electrons. This probably won't happen. Like, I meant it as a joke. This probably won't happen. Like, the normal charge for carbon is gonna be like 4 negative or 4 positive. This is the general charge for the whole. It was 1, 2, 3, 4A group. So, this I meant it as a joke. Okay, carbon will hardly ever have a charge of 2 negative. But like, just in case you're curious, carbon will never be 2 negative. But anyway, in this case, well, it will sometimes be, but not naturally. In this case, it gained 2 electrons because it has a charge of -2. So let's try to visualize this. Actually, you know what? Let's just assume the charge was -4, gained 4 electrons. So again, I'm not gonna do the nucleus. I'm just gonna do like this for the nucleus because I'm too lazy. Anyways, carbon's got like 2 core electrons and in this case 8 valence. 2, 3, 4, 5, 6, 7, 8. Valence is just the number of electrons on the outer shell, but we'll talk about that more later. So let's change this to 4 negative here. In this case, we know that in the nucleus there are 6 protons, so the nucleus will have a charge of +6 or 6 plus. Now, the outer shell, there's already 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait a sec. Oh, oops, that was not an electron. You see, my drawing was like so bad. It was like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. So it's 6 minus 10. And we get -4. That's the result we want. So let's try doing this backwards. For example, we know that the charge of a atom of carbon is 4 negative. In this case, let's think about it. There are 6 protons that canceled out 6 electrons. And then there are still 4 electrons left, not canceled out. So if we think about it, 6 plus 4 is 10. -10 actually. -6 plus -4 is -10. -10 is the charge of 10 electrons. Basically, practically, I mean, what we do is first, here's just a simple way to do it. Like, we see the charge. Let's assume the charge was 2 negative again. So we know that this atom gained 2 electrons due to the extra negative charge here. And a neutral atom of carbon would have 6 electrons. It gained 2, so it will have 8. And also in this case, it gained 4 negative here. It gained 4. It originally had 6, so it's gonna have 10 now. That's all for today. I hope it all makes sense to you. And next time we're going to be talking about energy shells. And if we have time, we're also going to be talking about electron configuration, but probably not. So that's all for today.